In our last lecture, we considered this feedback connection, and we studied the stability properties of its origin under the condition that both external inputs to the system are zero. Okay, so we established asymptotic stability under the condition that H1, the first subsystem, is strictly passive, and the second subsystem is memoryless and passive. And using this very simple relation that E1 transpose Y1 plus E2 transpose Y2 equals U transpose Y. In other words, since U is 0, this equals 0, plus plus using the storage function of H1 as Lyapunov function candidate, we obtained using Lyapunov's theorem the asymptotic stability of the origin of the unforced closed loop. Okay, and when the storage function of the first subsystem was radially unbounded also, the result we saw was global. Okay, so we had global asymptotic stability of the origin. Today we're going to extend that result, namely, we're going to consider again this feedback connection. Okay, again under the condition that the external inputs are zero. We're going to show that the origin of this system is asymptotically stable if either of the following conditions hold. Okay, either both H1 and H2 are strictly passive, either both H1 and H2 are output strictly passive plus zero state observable, or one of them is strictly passive and the other is output strictly passive plus zero state observable. Okay, so that theorem is theorem 6.3 in the text. So consider feedback connection of two dynamic systems. Okay, so by feedback connection we mean this topology, and our dynamic systems are labeled by H1 and H2. Okay, suppose that they are described by the following model: xi dot equals fi xi ei yi equals h of I xi ei, where I is the index. Okay, so it's either 1 or 2 in our case. I equals 1 or 2, and we assume, as usual, that the right hand sides satisfy this, that is, they're 0 at 0. Okay, for both I equals 1 and 2. Now, for this subsystems and for that feedback connection, and under the following situation where the external inputs are 0, that is the origin of the closed loop system when U equals 0, and U is our input vector. Okay, U1 and U2 considered together as a single vector. When U equals 0, it is asymptotically stable if one of the following conditions holds. Okay, one of the following conditions holds. Okay, so case 1 is that both subsystems H1, H2 are strictly passive Okay. 2. Both systems are output strictly passive, plus they're both zero state observable. Are output strictly passive and zero state observable. And case 3 is the mixture of two cases. One of them is strictly passive, the other is output strictly passive plus zero state observable. Okay, one of the systems is strictly passive and the other is output strictly passive and zero state observable. Okay. And furthermore, if both storage functions V1 and V2 for the subsystems H1 and H2 are radially unbounded, then the result can be extended to, that is, asymmetric stability can be extended to global asymmetric stability. Okay. Moreover, if both storage functions V1 for H1 and V2 for H2 are radially unbounded, then the origin of the unforced system is globally asymptotically stable. Okay, so the proof technique is exactly the same with what we did establishing our last result in the previous lecture. Namely, we're going to use the fact that that is 0, okay, U1 transpose Y1 plus E2 transpose Y2, because that equals U transpose Y, and U, in our case, is 0. Okay, so we're going to use that. We're going to use Lyapunov theorem to establish stability. For that, we require a Lyapunov function candidate, and Lyapunov function candidate for the overall system will simply be sum of the individual storage functions. Okay, and then by the definition of stability, excluding passivity, we're going to see that that new Lyapunov function candidate has a negative definite or negative semi-definite, depending on the case, time derivative, and then using Lyapunov's theorem or Lyapunov's theorem plus Lassalle's invariance principle, the asymptotic stability will be established. Okay. Now, let's go ahead with proof. Okay. As we said, the first step is obtaining a Lyapunov or constructing a Lyapunov function candidate, and this looks like a variable candidate v of x as the sum of v1 x1, first storage function for the first subsystem, and storage function of the second subsystem. Okay, v1 of x1 plus v2 of x2. Now, we know the following from our earlier analysis. In fact, from the proof of an earlier lemma 6.7, we know that each of those functions, okay, v1, vi or xi, let's call them, has to be positive definite, okay, because output passivity plus zero state observability requires that the storage function for the corresponding system is positive definite, or strict passivity directly implies that corresponding storage function is positive definite. Okay, so let's keep that in mind. So we know from that lemma that v1 and v2 are positive definite, respectively with respect to x1 and x2. Okay, so V1 is positive definite with respect to x1, and V2 is positive definite with respect to x2. Once again, that comes from strict passivity or opposite passivity plus zero state observability. Okay, so that's true for all these three cases. Okay, therefore, so this is positive definite with respect to x1, this is positive definite with respect to x2. Therefore, this v of x, the overall Lyapunov function canon, has to be positive definite with respect to the overall state x, which is x1 and x2 considered together as a single vector. Hence, v of x has to be positive definite. Okay, with respect to the state of the overall feedback connection x, x1 and x2. Okay, now what we're going to do from this point on is we're going to go case by case. So let's consider case 1, where both systems are assumed to be strictly passive. Case 1. So what we have is v dot of x less than or equal to something. So we know that v1 dot is less than or equal to minus psi1 of x1, where psi1 is a positive function of x1, plus e1 transpose y1, inner product of e1 y1. Okay, so that's v1 dot less than or equal to minus psi1 of x1 plus e1 transpose y1. Okay, so we have that for first subsystem, because first subsystems are supposed to be strictly passive. Likewise, we have it for second subsystem, where indices should be replaced by 2, because that's also assumed to be strictly passive. Therefore, we have this for both I equals 1 and 2, where psi I is a positive definite function of its argument. And then, if this is true for both I, you compute the dot for v times the root of v. So what v dot is v1 dot plus v2 dot, and each vi dot satisfies that. So we can write then for v dot as e1 transpose y1 plus e2 transpose y2 minus psi1 of x1 minus psi2 of x2. Okay. Now this sum, okay, equals the inner product of u and y. And u is 0 because we're considering the 0 external input case. Therefore, regardless of the output, this sum is always 0. Okay. This equals u transpose y, and u transpose y equals 0. And psi I is positive definite with respect to its argument xi. Therefore, we have obtained, thanks to our construction here, v1 plus v2, we have obtained v dot of x less or equal to minus psi1 of x1 minus psi2 of x2. Okay. Now let's define psi1 plus psi2 as psi. Therefore, we can write this as minus psi of x. X is our overall state, x1 and x2 considered together. Since this is positive definite with respect to x1, this is positive definite with respect to x2, their sum must be positive definite with respect to the overall state x. psi is positive definite with respect to the overall state x. Okay. Hence, we have v dot of x less than or equal to minus psi of x. Okay. So what they've obtained is that we have a Lyapunov function candidate which is positive definite with respect to the overall state, so it's positive definite, and we computed its time derivative and figured out that its time derivative is less than or equal to some negative definite function of x. Therefore, by Lyapunov's theorem, the origin is asymptotically stable. Furthermore, if both v1 and v2 are readily unbounded with respect to x1 and x2, that property will be inherited by v. Therefore, v will be readily unbounded with respect to x, and hence you would have, in that case, global asymptotic stability of the origin. Okay, so it's a very neat, clean, simple proof. Now let's consider case 3 and then case 2. You can work it on your own if you're interested, because the techniques are almost the same in each cases. Case 2 was both systems are output strictly passive and zero state observable, and case 3 was the hybrid case, the mixture. One of them is strictly passive, the other is output strictly passive and zero state observable. Now we're considering that hybrid case, the middle case. So for that situation, again, using the sum of individual storage functions as our Lyapunov function candidate, we compute the derivative. Okay, we compute v dot. Again, we have v dot less than or equal to this sum, which is 0. And in that case, case 3, we have minus psi 1 x1 and then minus a positive definite function of the second output y2. Okay, so v dot of x in that case would be less than or equal to minus psi 1 of x1 minus positive definite function of the output of the second subsystem. Okay. Where by definition of output passivity, we have y2 transpose rho 2 of y2 is never negative. In fact, it's always positive, except for the case y2 is 0. Okay. So that's true for all y2 different than 0. Okay, so we have that for v dot. And so what we have is, we have a storage function, we have a Lyapunov function candidate, and we stated that, we claim that, or we know that, that is a positive definite function of the overall state. Okay, so that's established from previous lemmas. And when one of the systems is strictly passive, the other is output strictly passive, the time derivative of that positive definite function is bounded by minus this function, where psi 1 is a positive definite function of x1, because the first subsystem is strictly passive, and this term minus y2 transpose rho 2 of y2, and that's positive definite with respect to y2. Okay, but that doesn't make it positive definite with respect to x2. Okay, but it turns out we don't need that. By using invariance principle, we can still establish asymptotic stability, even though v dot is not upper bound by a negative definite function of the overall state. Okay, how are we going to do that? So let us study the solutions that stay identically in the set where the time derivative of our given function candidate is identically zero. Okay. And if you can show that if a solution stays in that set identically, it's only possible that that solution must be the solution sitting at the origin, then we would have a spherical stability of the origin. Okay. So let's try to figure out the implications of a solution staying identically in that set. In other words, what does this condition, v del of x equals 0 for all times, implies? Okay. Now this is v del of x, which is upper bounded by this thing. This is never negative, therefore this is never positive. Likewise, this is never negative, therefore this is never positive. Okay, and this thing is 0. So this whole thing is never positive. So something that's never positive is larger than, because this thing is 0, is larger than 0. And that's only possible if this whole thing, okay, is 0. If this is 0, then this thing is also 0. And then what we have is this guy, this term is never negative, likewise this term is never negative, and their sum is 0, so that means individually this must equal 0 and this must equal 0. Okay? And that is just a simple implication of, consequence of the fact that v del of x equals 0. Now if this thing is 0, since psi1 is positive definite because the first subsystem is stupid, that's it, it means that x1 must be 0 identically. And this system, or this term being equal to 0, means that since it's positive for all non-zero y2, there's only one possibility that y2 must be 0. Okay. So, if, therefore, v dot, the solution satisfies such that it remains identically in this set v del of x, it means that x1 of t must be 0 for all times, and y2 of t must be 0 for all times. Okay, and from that we will try to reach that x2 must be 0 for all times, so that we will have the asymptotic stability. Now, y2 being identically equal to 0 implies that E1 signal must be identically 0. Why is that? Because, remember the connection, this is H1, this is E1 minus plus, this is Y2, and this is U1, okay? Now, the input is 0 because we consider that case, hence E1 is minus Y2. And what if Y2 is therefore if identically 0, therefore automatically E1 is identically 0. Then what? What we have is E1 identically 0 and x1 identically 0. And that implies what? This is our first subsystem, the output of which is y1. Okay. Now what's y1? y1 is h1 of x1 e1. Okay. h1 is the output function of the first subsystem. Now e1 is 0, x1 is 0, and this function h of 1 is 0 at 0, therefore the output of the first subsystem must be identically 0. Okay, y1 must be identically 0 because h1 0 0 equals 0. Okay. Now, if y1 is 0, that means because u2 is 0, e2 is directly equal to y1, and therefore e2 equals 0. Just from our feedback topology. Okay, because e2 and y1, they're the same thing when the inputs are 0. What else? Also, e2 identically 0 and y2 identically 0 implies that x2 is identically 0. Okay. Now, okay, so why is that? Because y2 is h2, x2, e2. Okay, so e2 is the input to the second subsystem, and we know that the second subsystem is zero state observable. So that means when the input to that subsystem is 0 and when the output is 0 identically, then because the system is zero state observable, the state of the system x2 must be identically 0. Okay, so that's by zero state observability of the second subsystem. Okay, therefore, the only solution that can stay identically, meaning for all times, in the set b dot of x equals 0 is the trivial solution. Okay, so once again, this implies x1 equals 0 immediately, and also after a few lines of reasoning, we also obtain that x2 must also be 0. So both x1 and x2 identically equal 0, so that means our state of the overall system, which is x, must be 0. Okay, identical. By trivial solution, we mean the solution that remains, that sits on the origin for all times. Okay, and then the result follows by the invariance principle. Lassalle's invariance principle. Corollary 4.1 from the text. Okay. And then the case 2, where both systems are output passive, can be demonstrated in a similar way. Again, we will be using the stored Lyapunov function candidate as the sum of individual storage functions of each subsystem, and the result follows similarly. Okay, now let's apply this theorem to an example and establish a stability of the following collection of systems. Example. Okay, let us consider two subsystems connected through feedback. H1 reads x1 that equals x2, x2 that equals minus a x1 cube minus k x2 plus E1, which can be considered as the input to the first subsystem. And the output of the first subsystem is the second state variable, okay, x2. And as for the second system, H2, we have the following model: x3 that equals x4, x4 that equals minus b x3 minus x4 cube plus E2, which is the input to the second subsystem. And the output is x4 for the second subsystem. Parameters a, b, and k, they are positive constants. What we ask is, suppose that these two systems with inputs and outputs defined as E1, Y1, E2, Y2, they are connected through feedback, and you try to figure out the stability properties of the origin of the closed loop, which is of order 4, because it's a second order system. It's a second order system, therefore the interconnection is 2 by 2, fourth order system. Okay. Establish for those subsystems the global asymptotic stability of the origin of the feedback interconnection. That's achieved through E2 equals minus, E1 equals minus Y2. And E2 equals first system's output. Okay. So what's being done is this Y1, you take it and connect it to the second subsystem. So the second subsystem sees Y1, the output of the first subsystem, as its input, and then you take the output of the second subsystem, negate it, and feed it to the first subsystem. Okay, so the first subsystem sees minus Y2 as its external input, driving input. And now that connects the loop, and we will try to figure out global stability of the origin of that closed loop. Okay. Solution. We can do that by passivity, and for that we have to show what types of passivity properties do these subsystems possess. So let's work with the following storage function for the first subsystem. V1 equals a over 4 x1 to the 4 plus 1/2 x2 squared. And with that storage function, let's look at its time derivative. So we have V1 dot equals a x1 cube x1 dot plus x2 dot. Okay, x1 dot and x2 dot, they're here. Let's write them down. Equals a x1 cube x2 plus x2 times x2 dot, which is minus a x1 cube minus k x2 plus E1. Okay, this term and this term, they cancel out. In fact, we want them to cancel out. That's why we have chosen such a storage function. And what we're left with is minus k x2 squared plus x2 times E1. E1 is the input, x2 is the output. So what we have is minus k times y2 squared plus the product of output and input for the first subsystem. Therefore, first subsystem is output strictly passive. Okay, so that equals minus k y1 squared plus y1 E1. Hence, the first subsystem H1 is output strictly passive. So let's call that fact or discovery as A. And then what else? Let's also analyze, investigate the observability properties of first subsystem. Okay. For that, what we do is we set both the input and output of the first subsystem identically as 0. And then we see the consequences of that condition on the remaining states. So when E1 is identically 0, E1 is the input to first subsystem, and Y1 is identically 0, that's the output of the first subsystem. That means, first of all, X2, the second state of the first subsystem, is identically 0 because the second state is no other than the output. Okay? This and that, they're the same. Now what we have is X2 is identically 0, so it's constant at 0. So clearly, because it's constant, X2 dot must be identically 0. Okay, so what we have here is, this is 0, this is 0, and this is 0, therefore X1 cube must be 0, and that's only possible when X1 itself is identically 0. X1 is identically 0. Okay. Therefore, when both input and output of the first subsystem are identically 0, then both states are identically 0, and hence the first subsystem is 0 state of 0. Hence, H1 has to be 0 state of 0. And let's call that discovery B. Okay, or fact B. Now let's consider the second subsystem. Okay, H2, which is here. For that, let us work with the following storage function candidate. B2 equals B over 2x3 squared plus 1/2 x4 squared. Okay. A positive definite with respect to the state of the second subsystem function. And then that yields V2 dot equals Bx3 dot plus x4 dot. X3 dot, x4 dot, they are here. So let's write them down. B x3, x4 plus x4 times x4 dot minus B x3 minus x4 cube plus E2. This and that, they cancel, and what we're left with is minus x4 raised to the power of 4 plus E2 times x4. x4 is the output of the second subsystem, therefore we can write this as minus y2 raised to the power of 4, and this, observe, is a positive definite function of the output y2, and we have minus in front, plus the product of the input and output of the second subsystem. Okay, so that implies the second subsystem is output student passive. Okay, discovery C. Okay, what else? We also have to establish zero state observability if you want to use the previous result for the second subsystem, and that's easy when E2 identically equals 0 and Y2 identically equals 0. We have x4 identically equals 0 because x4 is the output. This comes automatically. And then x4 dot must be identical to 0 because this is constant, hence its derivative must be 0. And if you look at the x4 dot equation in the system, this is 0, and the input is 0. That's only possible when x3 is also identically 0. So this yields x3 is identically 0. So therefore, both input and output of the second subsystem identically 0 implies the state of the second subsystem is identical to 0. Therefore, H2 is 0 state observed. Hence, H2 is 0 state observed. Okay, observation D, or discovery D. So what we have is A, B, C, and D, and that's enough to claim that the origin of the closed-loop system is asymptotically stable. But we're asked for global asymptotic stability of the origin. Therefore, we require one less piece to the puzzle. And that's easy because by looking at V1 and V2, we see that V1 is radially unbounded with respect to its own state x1 and x2, and V2 is radially unbounded with respect to its own state x3 and x4. Therefore, the sum V1 plus V2, which is our overall Lyapunov function V, is radially unbounded with respect to the overall state x, which has variables as x1, x2, x3, and x4. Okay, finally, note that both V1 and V2 are radially unbounded, which makes V radially unbounded. Therefore, putting all those pieces together, A, B, C, D, and E, and remembering the last theorem that we have established, we can claim that the origin of the closed-loop system x, x1, x2, x3, x4 equals 0 has to be globally asymptotically stable.